Hey, welcome back, my fast physics students. I'm going to do a circular motion problem for you. And what I want to do is I want to look at something that you would experience in everyday life, but you wouldn't sort of intuitively know how it works exactly. And that's the idea of driving your car around a corner. So when you're driving your car around a corner, what's going to happen is you're going to be moving along, and I've actually pre-drawn this car for you right here. You're going to be moving along a straight line, and then you're going to come to this turn, right? And so what's going to be happening as you go through this turn? Well, this ends up causing a circular motion, right? And so your car then has to be given some kind of an acceleration toward the center of this circle, right? And so if this is the oh, look at that. I start using these tools and get straight lines, and all of a sudden I can't even draw a straight line. I probably could never before, anyways. But you need to have something that accelerates you toward the center. And so what's going to cause you to be accelerating toward the center? Well, the actual cause of making you able to turn is going to have to be a force, then a net force that is toward the center of the circle. And so where is that force going to come from? Well, that force is going to be on your tires. And so I drew myself another car. So as we go into this turn right here, we're going, and as we turn right here, the force on our tires, that's why we turn our tires. The road, actually, when we turn our tires, the road pushes on our tire back, right? It's Newton's third law of motion. For every action, there's an equal or opposite reaction. So the road is actually going to push back on your tire. This is the tire I drew. You can tell that I took some extra time to draw it because it's really good. But so that is what we call centripetal force. So the force of centripetal, in this case, as you go around a turn, is going to be the friction of the road on the tire, which is in the direction of the center of the turn. And so as long as the road is providing a friction force toward the center, a centripetal force, then you'll turn. And that's why you turn your wheels. And so if you don't turn your wheels, then the friction force is right here, and you don't turn around. When you don't go around the corner. When you turn your tires, it angles the tires in such a way that that the road pushes back that way, because with the angled tire, you're pushing at the road at an angle, so it pushes back at the same angle. And so then you turn your wheel in reference to how much you need to go around this turn. And so what I want to do real quick is I want to analyze this idea of when we go into one of these turns, oftentimes there's these signs and it says, a lower miles per hour than what you're going. And so in this physics problem, I want to sort of essentially have Mr. Newton teach you the physics behind why being stupid sometimes makes you die. So say you're going into this turn and you say, you know what, this 20-mile-an-hour thing, it's just a suggestion. I'm going 80, so let's say that you're going 80 miles per hour, right? So you're going 80 miles per hour, and so you think, I don't need to slow down. I mean, that's just a suggestion. Um, I'm going 80 miles an hour, and I'm an awesome driver, and I'm just pure awesome as it goes. And let's say on the other side of this is, a cliff, and there's, death-defying rocks and trees, and so that's what they look like. This is a stick drawing of death-defying rocks and trees, and so it looks scary. So so if you go flying off of this cliff, you're going to die. So say you're going 80 miles an hour. So let's see what happens. Let's get a couple other numbers right here. I looked up actually the coefficient of static friction. So the coefficient of static friction on a tire in dry weather on a normal tire with treads is going to be a maximum of 0.7, right? So that means that as soon as you exceed that 0.7, it's going to turn into a coefficient of kinetic friction, which essentially means you're going to start to slide out and over the cliff. And so when you're going around a turn, you want to keep your friction static. You do not want it to be kinetic. And you remember that the difference between static friction and kinetic friction is just simply that this means it's not sliding, and this means it does. Um, so you don't want this. So that essentially, when you switch over to kinetic, it means you're skidding along, and that's not what you want. All right, so let's analyze this problem real quick. So let's say that your car is about 1,500 kilograms. That's a pretty fair estimate for most cars. And so let's sort of just kind of run some numbers here real quick. So what is going to be your acceleration of centripetal needed for you to go around this turn at 80 miles an hour? So 80 miles an hour, and we don't really use that in science, so we're going to have to convert that to meters per second, is about 36 meters per second. So 80 miles an hour is about 36 meters per second. So let's use that. So the acceleration of centripetal is going to be the velocity squared divided by the radius. So my acceleration of centripetal is going to equal 36 squared divided by my radius is 50 meters, right? So I got the this is about half a football field, so it's a good big huge turn. It would look like you might have plenty of room to turn even if you're going faster. All right, so what does that give us? So if we calculate this out, that leaves us with an acceleration of centripetal of 25.92 meters per second squared. All right, so what are we going to do with that? Well, we need to figure out the force here. Now, all of the force that's causing the acceleration of centripetal is going to be this force of centripetal, which we just talked about. The only place that the force is going to come from to push your car toward the center is going to be from the road pushing back on your tires because you've turned the tires in the opposite direction to the road, and so the road pushes back. So all of your force is friction force. So your force of centripetal, or your force net, in the centripetal is going to equal your mass times your acceleration of centripetal. So let's figure out what that is. So my mass is 1,500, right? We just figured out that my acceleration of centripetal was 25.92. So what's that going to equal for force? So my net force here is going to equal 38,880 newtons. Wow, so that's a lot. So now let's sort of figure out what that means then. So if that's my force, and that's all coming from friction force, I could say that this is my needed friction force to keep me from skidding. And so what sort of a coefficient would I need? Now I know that actually if I exceed my 0.7 coefficient, I'm going to run off the road. So let's see if I can make this turn going 80 miles an hour with a 1,500 kilogram car and normal tires on it. So we're gonna go ahead and throw this 38,880 number in here, and so we know that the friction force, right? Friction force, sorry, equals the coefficient of static friction times the force normal. Oops, I put an M there. It should be an M, not the force normal. Not quite sure what the force normal is. Maybe it's a cult of normal. So here's what we're going to solve for. We're going to solve for this coefficient of static. So what's our force normal? Our force normal is going to be the 1,500 kilograms times gravity, right? Because that's the actual force that my tire is going to be pushing down, with gravity. It's my force normal. The road is the perpendicular force against my tire, and so my tire is going to have the force of that car on it. Okay, so, or at least all of my tires together are going to have that force. But let's just look at it in general. So what about my friction force? So I have my force normal being 1,500 times 9.8, and so I divide that by 38,880, and that gives me a coefficient of static friction of 2.64. Now, even if that was divided amongst two tires, likely it's just the outside two tires. Even if that was divided against two tires, you see there's no way I'm going to make that turn. Because if I start to exceed 0.7, right, I'm going to start to skid. So that is not going to work. I'm gonna fall off the cliff and I'm gonna die. All right. So where is it that they come up with these sort of numbers when they recommend us driving a certain miles per hour over the thing? Well, let's go ahead and just figure out. Well, then what is the maximum velocity I can go around this turn? And so to do that, I would just work backwards. I would say, well, I know that my coefficient can't exceed 0.7. So I would say, okay, so what is my friction force going to be if my coefficient of static friction is 0.7, right? And I know that my force normal is going to be 1,500 kilograms times my force of gravity, 9.8. So that's going to give me a force of friction of 10,290. So this is the maximum force of friction that I can have to go around this turn, right? To go around this turn and not slide off the cliff and die. So let's go ahead and throw that number then, and then work backwards and find out what would be the maximum velocity around the turn that I could do. Okay, so what I want to do now is I want to solve for an acceleration of centripetal. So I know that the force of friction is going to equal the mass times the acceleration of centripetal. So I'm going to go ahead and say my mass is 1,500, and I want to solve for my acceleration of centripetal. So if I divide that by that, I'll find out that my new acceleration of centripetal equals, let's see, I calculated this out, 6.86 meters per second squared. So that's a big difference there. So this is the maximum I can have without, falling off the cliff. Well, acceleration of centripetal we know equals velocity squared divided by the radius. So I can take this acceleration of centripetal and figure out my velocity, because my velocity squared, and I know my radius is 50 meters. So go ahead and multiply 6.86 by 50, and then take the square root of that, and I'll find out that my velocity, my maximum velocity to stick on the road and not slide off, is 18.5 meters per second. And so if you want to know what that is in miles per hour, it's 41.4 miles per hour. So the idea is if I exceed 41.4 miles per hour around this turn, I am going to start sliding off and die. Now, you might say, well, then it says 20. Okay, why does it say that? Well, not everybody has maximum grip tires, and also this is the coefficient of static friction for when the road is dry. When it's wet, it changes drastically by about half. So you're looking at something around 0.4 or 0.5 if it's wet. So the actual road condition changes. So we got to have a number here that is going to allow us to stick on the road safely when the road is wet or when the road is dry. So that's where they come up with these sort of recommended speeds as you go around. They've taken into account all of these factors, and knowing that it's friction force that keeps you able to go around this turn. And all of this is circular motion, and circular motion incorporating forces and friction force as you go around a turn. So hope that helps and gives you sort of an idea of how to solve using the two formulas that we discussed in the last video, which is the centripetal force right here, which is Newton's second law, essentially just adapted, and then the acceleration of centripetal right here, which we derived in the last video as well. So just all we did was use these two things to sort of prove and figure out if going 80 miles an hour is going to work to go around this turn. All right, well, I hope that helps.